by then, however. And today, with a fully stable release of both Akka Streams and Reactive Streams being included in JDK 9, which is going to be released very soon, this is a kind of accumulation of all of the efforts of the last years. So, who am I? I'm Konrad Malawski, Ktoso. You may know me from Twitter or something. And yeah, I work at Lightbend on the Akka team. That's some conferences and technology things I do in my homeland, Krakow, Poland. And why am I talking about Reactive Streams? I contributed the majority of the technology compatibility kit there. So that's kind of why I care about this a lot. So where is Akka being used? All over the place, in technology companies and banks and all kinds of fields. So anyone who doesn't know what Akka is? Okay, 2 people. So Akka is really for building distributed and concurrent applications. So if you just need concurrency, you can just use actors. If you want distribution, we have clustering, we have HTTP. So really you have a full kind of toolbox. You can pick and choose whichever part you need to use, right? So here's the list of modules, actors being the concurrency part, persistence if you need to do event sourcing, HTTP if you need an HTTP server, that is actually streaming enabled. I'll explain that during the talk, and many other modules. So let's talk about streams, because what is a stream really? And well, like I said, 2013 we kind of do reactive streams. However, there also exist these technologies which have stream in the name, or at least allure somehow to the word stream. And the problem is, like half of these technologies you can't even compare directly because they do completely different things. So let's try to solve this problem. So what do I mean, and what does reactive streams mean, and any implementation thereof when the word stream is used? So it's most importantly about infinite data sets. So it could be time, it could be you just listen on some incoming connection and you get more weather data or stock exchange data. It's something live and coming in at some rate. It's element by element, so we don't talk about random chunks of elements. When you get an element, it's a specific thing you can do things with. And really it is asynchronous because that's how we get the scalability benefits, and really streaming is all about scalability. So there's this new trend, fast data. It's kind of a pun on the big data word that was being used in the recent years. A usual Hadoop infrastructure or kind of application architecture looks like this, right? You have some pieces that hold the data, and you have your Hadoop cluster that processes the data, and by the end of the day or in a few hours you have some kind of aggregated result. So the problem is, well, this is kind of slow to give you responses. So both streaming and the fast data architectures basically want very similar things. However, we want them right now without long delays to get the response back. So this is a kind of architecture overview we designed at Lightbend to kind of explain where all the pieces meet. Because, yeah, you can use Kafka for ingestion of data. However, you also very often actually use just an Akka or Play endpoint to get requests from people, and this is also incoming data, right? Or someone else is uploading sensoric data to you. That usually goes over TCP or HTTP. So ingestion points are very different. And then where you respond is also sometimes different. Some data can be responded later on, so you can actually do it in Spark, but sometimes you can't take the latency of that. So let's talk about where does Akka Streams fit. So it really is designed for being right away in the hot path of your request. Compare that to, for example, Spark streaming. It's more like you submit a job, the job runs, it did something, right? Akka Streams is more on the side of, inside of your request, you have to do some streaming things and reply right away. So really small and focused. What we will have in JDK 9 is basically reactive streams. We'll talk about reactive streams during this talk. And in there it will be called flow, but whenever you will see flow in a code base, that is reactive streams. So the Java util concurrent flow. I kind of took the naming from what we had in Akka. So that was streams, but what is actually reactive? So I wrote a mini book. There's a link later on in the talk to the book. It's like 20-30 pages that tries to explain all the different trade-offs. You can download it for free. But for anyone who hasn't seen what reactive is, there's a manifesto. It's also translated to Japanese, so you can read it in your native language. And it's about really building solid foundations, mostly around the message-driven stuff, but really they relate one to another. So we have these reactive applications, but that's only a part of the pie. Because what we really care about is, okay, the entire system should be reactive, and then we actually get some benefits out of that. So what does Reactive Streams address? It really focuses on those two things, which is the message-driven and the responsive side. Does it address resiliency? Yeah, somehow, if you squint, but elasticity is not really something Reactive Streams does at all. So how does Akka fit into all of this? Like I said, it's a toolkit, right? So if you need elasticity, you take Akka cluster, you have your elasticity. If you want, streaming, you take streaming and you have these things. And if you want resiliency, we have failure detection in the cluster, etc. So it really, whatever you need, you just pick the right pieces. So this is also the different trade-offs we can do inside and outside applications. Because outside, we communicate with any kind of arbitrary system. So, for example, most of the time this will be some RESTful or HTTP calls. Most people will want either XML or JSON, and that's actually pretty slow. Whereas on the inside, we can do way better in our responsiveness story. So responsiveness, very much related to performance. Inside, we can use binary, really fast messaging systems like Akka's remoting or anything else. So it's different trade-offs. However, let's look at a not quite reactive system, which is where this entire story started. So it's back then TypeSafe, before we renamed to Lightbend. The usual story of a customer that would use our technology is they write their new application. It's actually working really well. It's handling the traffic. It does many thousands of requests per second, etc. However, a system is never really alone, and it always has to talk to some other system, be it inside the company, some other Teams service, or outside the company, some API that has quotas or something else. And what would happen often is, well, because they do, the blue team just wants to go as fast as they possibly can, right? The problem is they overwhelm the other services, right? So either you exceed quotas, or you just start hammering the other service so it becomes unresponsive. So this is what I mean by a reactive application is not really helping, because we have one reactive application, but in the grand scale of things, now we caused problems to other people. So best practices are solutions to yesterday's problems. What would people recommend in these situations? I'm sure you recognize this pattern. So I send some requests, the server is overwhelmed, so instead of producing an actual response, it produces a service unavailable response. So this is a way of throttling, right? But it's not really flow control, because you can't control the guy sending you the request. You can just tell him, hey, I can't possibly answer so many questions at the same time. So this is circuit breakers. I mean, we have circuit breakers in Akka. Another circuit breakers library you probably know is Netflix Hystrix, very popular, like it a lot. But does it really solve the core problem? Not really, because we do an exponential backoff, we wait a bit, and then we try to send a request again. But it's kind of like having this car and then driving into a pole, and then you have the car again, the circuit breaker is open again, and you drive it into the car again, and you have it again, and we kind of bring the system to a crash, and only then we realize, okay, let's wait a bit. Wouldn't it be nicer if you don't have to crash a system before kind of backing out a bit? So circuit breakers, awesome. Specifically, they're good for handling failures. What if that other system is really failing? But it's not as good as just controlling the flow. So is there a way we can get rid of the guesswork? Because here we're kind of guessing, okay, can I send this request? Will the guy be overwhelmed or not? People do client-side quota tracking or some other technologies, but it's still guessing. So we can do better. And we need some shared semantics to do that, right? So the client and server have to have some protocol they both understand that they can communicate with. So that's Reactive Streams. That's kind of the reasoning why we need Reactive Streams. And it's really an SPI, so a service provider interface, rather than an API. I'll explain that in my following slide. So it's not really, when you go home today, you don't need to implement Reactive Streams. It's done. Okay, it's been implemented 3, 4, 5 times. People have implemented Reactive Streams. You should kind of know, okay, Akka Streams and RX, they implement Reactive Streams. And you can assume that this stuff just works, and then you use a library that implemented that. So a specification. So the reason it is a specification is because we have multiple systems, so it doesn't help if I only solve it in my application, right? We need it to work across applications or across libraries, right? If someone implements a database driver using Reactive Streams, I still want to be able to use it with Akka Streams directly without each time writing some conversion logic. So this is why we needed a standard there. So the solution to the kind of overloading the downstreams problem is basically back pressure. This is a terrible joke, which, I don't know, I find it funny. So it's not back pain, it's back pressure. But I always have to explain the joke, so I should probably drop it. But flow control, right? So we need some kind of flow control, and specifically we need flow control on the application layer. Because on the network layer, let's say you use TCP. TCP has flow control, right? It just has it. But it doesn't stop us from doing silly things in the application, right? So we want a similar concept as the TCP window mechanism on the application layer. Quick story how we started on that, how it ended up looking like that. So Play had something called iteratees back then, was solving the problem, but was difficult to use. In Akka, we had something in Akka.io. It was very low level, so not that useful unless you were directly working on TCP, which not that many people do. And when Ben Christensen started working on RxJava, he, back then, didn't really focus on back pressure, but he had a really nice API. And then he figured, yeah, we need back pressure as well. So we got talking, and we realized that all of us had kind of different pieces of the puzzle. Ben had a nice API, we had a nice high-performance implementation for TCP, Play had some experience with actually doing it in a real framework. So then fast forward, and it's already merged into the JDK. That was just, you can refer to the slides afterwards. So, what does it do? So it tries to solve this exact problem. You have two people, or processes, or threads, or actors that send messages to each other. It could be also different systems, right? And the problem is if the downstream, so the guy we send the data to, is slower at processing than the upstream. The subscriber has some kind of buffer, right? It keeps the messages in the buffer because this is asynchronous communication. It has to buffer somewhere. And yeah, what if this happens, right? So in asynchronous systems, it can and will happen unless you employ some flow control. So what can we do as a naive solution? Well, we can drop the messages, which is an unpopular answer. However, it's a trivial answer to both implement, and it's also present everywhere on the network layers, right? This is what TCP does if buffers overflow, and it will request resending data, right? This is what other technologies do as well. So it requires resending data if it was lost. That's, however, costly, because then we force the person sending the data to still have it, because it may be asked to resend the data. The other solution is to try to increase the buffer size, but you can't really do that infinitely because you're bounded by the amount of memory on the machine, right? So at some point, you'd overflow anyway and be out of memory. So, Reactive Streams in a single slide. It's this protocol where the subscriber processes messages asynchronously. So each of those arrows is asynchronous, right? So the processing is asynchronous. Here the requesting of data, I request 3 elements, is asynchronous. And the sending of the data, so 3 elements are being sent, is also asynchronous. So the entire protocol rides on the assumption of the producer of the data, the publisher, may never send more data than it was asked for. So we know, okay, my buffer has exactly 3 slots, I will request 3 elements, and this causes the buffer never to overflow. Because all of these arrows are asynchronous, you don't really have to ever wait for someone with a blocking of a thread, right? So this is how the interfaces look. This is what I said that you don't have to implement, but if you're curious. And sometimes you may see people presenting reactive streams. I don't know, maybe you have, maybe you will, because it will be in the JDK, so people will be talking about it. What they omit to mention sometimes, to my great kind of sadness, is the second point, that it's an interop interface. So it's really for interoperating between various libraries and systems. So do you have to manually implement these? Not really, because so the interfaces are simple. It's 7 methods, very simple methods, but there is this wall of text of different concurrency rules when you're allowed to call which method and with what synchronization guarantees. So you should be aware of reactive streams, but not implement them. You should just use them, right? Okay. So, reactive streams already made an impact. So I said that Spark is different than reactive streams. Did reactive streams help Spark? It actually did, because what we had a number of findings during working on reactive streams, and our Spark team, so people contributing to Spark, implemented a number of rate estimators and kind of a back pressure mechanism inside of Spark that is inspired by what we found in reactive streams. So even though it's not directly related, we are very much collaborative and trying to help each other out, even though it's slightly different. If you know the language called Elixir, popular with Erlang people nowadays, I sat down with the author of that, and they basically ported a lot of the Akka Streams concepts over there. So it's nice to see that we inspire a lot of different technologies and that it's not just, okay, yeah, Akka did something fun. So, finally, the implementation. This is how it looks in Scala and Akka. So the prime kind of difference to actors here is that you have static typing. Everybody who knows Akka knows that the static typing is not that present. Here we are fully typed. However, we are also very restrained in the layouting. So you have to construct the full graph and then you run it. There's also some more advanced tricks you can do. In actors, you can completely dynamically start and move actors around different distributed systems. So it's slightly different, but yeah, it is typed. So the prime wording we're going to use is a source, a flow, and a sink. This is pretty much easiest visualized as having one input, one output, or both, right? So one input is a sink. So this is where the data flows. It is a terminal point, so nothing can come out of a sink. So it would be a file, for example, or something like that, or a database, or etc. If you want to go really advanced, you can arbitrarily shape any kind of graph. So, for example, something that zips together a person's age, surname, and name into a person or something. But it's still going to be asynchronous and backpressured. So, now, what we try to solve with this Akka Streams approach that is different from this other streaming things is let's say your app has some kind of requirements, and it's usually somehow weird. A lot of the parts are maybe similar. You need, oh yeah, I have this HTTP thing. Yeah, everybody has some kind of HTTP thing, but there's always something, you have some different requirement, right? So, because Akka is not a framework, we don't just magically fit into all of your needs. We just don't. So what we do instead is we provide many small building blocks that solve small problems, and then you can pick and choose from these small building blocks that still compose together. So I'll show the composing in a second. And if you have something that's really weird, like really specific to your application, you can write it yourself pretty easily, and it still fits to all the other connectors. This is the abstract version of it, and there'll be a hands-on example of that. So instead of just implementing all kinds of stuff in Akka, we make it both possible and easy, and we foster a community around connecting different stuff. The code name of that project is Alpaca. The Alpaca project doesn't have an artifact. You can't just download Alpaca. It's this community of projects, right? So some of the projects we actually maintain. So inside Akka, that's these integrations here, File.io, Java Streams interop. Some other technologies, so for example Kafka, the Kafka integration with Akka is maintained by Krzysiek. He has a talk in this room at 3:30. So if you want to learn all the details about the Reactive Kafka implementation, go to that talk. And what you should remember is that this is an open thing, right? If there's something that you miss, should be there but isn't, open an issue on the issue tracker or implement it, and then we add it to the list. And yeah, we also do some integration patterns. So let's see this in action, right? So we know streams and HTTP, and quick reminder, we talked about TCP, but we remember that it's actually a streaming protocol. To clarify, because TCP again has a different kind of definition of the streaming here, what TCP talks about is basically ranges of bytes. You have this stream of bytes, and you are receiving up to a certain point of that infinite stream of bytes, right? And it has the flow control implemented in terms of these bytes. It's not talking about requests or anything, right? That's, for example, HTTP or something on top. However, what we do in Akka is we take this back pressure from the TCP layer and we actually expose it all the way through the entire stack to the HTTP server. And the HTTP server is a flow of HTTP requests to responses, actually an entity, so an HTTP entity, if someone uploads your data, it's a source of bytes. So again, it's a stream. And what we can do with that is if someone goes into a tunnel and stops receiving data on their phone, let's say I'm Twitter and I'm receiving tweets on my phone, I go into a tunnel, so I stop reading from the TCP connection. This will actually stop the HTTP server generating the tweets. It will not generate the tweets for the client because it sees, hey, the client is not even reading the tweets, so we don't need to generate them. And this is completely transparent. Again, WebSockets are a flow of message to message, and TCP actually, because I kept talking about it today, so what is TCP? TCP is a flow as simple as that, right? And they stack. And they all speak the same protocol, it's all reactive streams, it all connects. So, let's have a demo. One of the fun use cases is when you really have to reply to some incoming stream of Internet of Things measurements. And when people talk about Internet of Things, they sometimes talk about the end kind of consumer, like my watch or something, your smartphone. Yeah, that's interesting, but the more kind of amounts of data are really in factories and in these robotics thingies that report all kinds of measurements, how it's performing. So for example, I got a friend to get me some data from a real system like that. and it basically reports the movement, so X, Y, Z axis movement of a specific robot, of all of its hands and its acceleration values, etc. So we have real incoming data from such a robot. We slap it into Akka HTTP or different Akka things, and then we just use some machine learning stuff inside of that service right away to reply if we predict if that robot is misbehaving or not. So previously we teach that machine learning model, usually a different team does that, and then you have the model inside of your application and just predict if that machine is going to break or not. So you can fix it before it destroys the car by accident. So this is an actual project that I got the data from. Let me show you the data maybe first, so we know what we are going to look at. Cut data. So this is from a specific day. And basically here you just see, okay, it says acceleration on the y-axis, all of these different values from the robot, right? And a lot of numbers. So we're not going to look at the numbers because that's meaningless to us. However, and we're still good on time actually, I think. So, is this big enough? Hi, yeah, hi, okay. So, very quickly, let's say you have your machine learning thing. So what the team working on that would do is they just say, hey, we need doubles, we will give you predictions. They give you this flow. What you do in the application then is, okay, I have my data points. What are data points? Let's see what a data point is. Yeah, a data point is a source of doubles. Okay, where do we get the doubles from? Measurement lines, incoming bytes. So it's just a source of byte string that we then put via a framing, and then we decode it into the actual numbers. Okay, so just remember that. And now I want to kind of showcase this fitting together thing. So, okay, this is the code that we need to write to, yeah, maybe this much code. So you have the data points via CSV support because it's a CSV file. And this is just so we have a continuous stream of numbers, then via machine learning, and we just ignore the result in this example because I was logging it. So remember this part. Now, let's say we want to do the same, but like in my example I showed, yeah, the machine is reporting us the metrics. So how much do I need to change in my application to make the same system work from an HTTP incoming data? Basically, we write an HTTP server in 3 lines, so it's a post, it gets the entity, and what is the entity? It's a source of byte string, and it gives us back the doubles. This is again exactly the same. Framing, CSV support, so exact same code. And then we just run it here in the HTTP server. Again, the actual logic, exactly the same. And it handles all of the flow control, all of the back pressure. What if you want to use it from Kafka? Again, same thing. You just need to configure Kafka a bit, but this will be talked about in the Kafka talk in a few segments. So what we would do here is take the data from Kafka, make it measurements, scoring flow, done. So again, it's about the composability that you don't need to change anything in your logic here, depending on the data source. But it's still all streaming, it still connects. So, and there's 2 styles to do that. So if you've maybe coded a bit of Akka Streams, I just wanted to highlight that you can do two styles of API. One is you take a source and you emit a source. This is actually a bit worse than just giving people a flow, right? If you think about it, the first style is you decorate the source with your parsing logic, right? This is the framing, this is the CSV support that changes the byte string into doubles, so it's still a source. But instead you can provide people with a flow that will do a transformation from these byte strings to these doubles. So it's kind of like giving people a function, but it's streaming. Okay, so we demonstrated that it's pluggable, reusable, etc. So it's really backpressure in real systems. I usually have a demo of showing it off, but we don't have that much time today. It really shows on the TCP buffers inside the operating system that we stop reading from it, for example. Catch me later if you want to see that in action. So, and not only that, but remember the kernel, right? We want to go as fast as possible, but not faster. So there's another thing about that. So we want to go fast and understand what the hell is going on in the system. So this is really monitoring. So this is a company we bought maybe 2 weeks ago. And when you think about all of these connections, that's exactly what we have in Akka Streams. We have information about what is connected to what. We can do graphs like that. And then we can highlight which part of the graph is actually behaving slow or having failures. And this is something we'll be working on this year. So there'll be really nice monitoring features like that. That's ops clarity, but since we bought them, I guess the name will change. It's a bit chaotic right now. So, can you adopt this right now? You can totally adopt it right now, even though the JDK 9 isn't released yet. This is because when you use Akka Streams or some other implementation, you don't really touch the Reactive Streams interfaces. And what happens is it is really a verbatim copy of the same interfaces into the JDK, and the only change is the package name. So it used to live under org Reactive Streams publisher, so now it will live under Java util concurrent flow, right? So that's the only change between Reactive Streams and JDK 9. So there's no need to wait. So if you would like to find us, maybe help contribute, or just ask questions. So for questions, the best place is the Akka mailing list. So that's Akka user, or the chat room. So Gitter IM, Akka. If you want to use Akka, have some questions about it. Me and the team hang out there. And I'm actually going to be in the Japanese time zone soon. So you can just chat with me during the day. And if you want to contribute things, the Akka dev channel is if you want to submit maybe a connector to some other technology that we don't have in Alpaca. So, last point about, you probably are curious what's going on in Akka and what the next steps are. So 2.5, we've started releasing milestones for it. So the milestone 2 was released yesterday. It is binary compatible with Akka 2.4 and Akka 2.3 actually. So this is a big achievement for us. You can just upgrade the version number and don't need to worry about any incompatibilities. Distributed data, so it's CRDTs, highly available, fast CRDTs, are getting stable. Persistence query, so again, if you're doing event sourcing, it's getting stable. We're working on Alpaca connectors, so you saw a slide with various technologies. It's going to be even more. I'm specifically right now working on Akka HTTP to implement HTTP 2 support. That's going to be very interesting. And something that people have been asking for since the first talk I did here in Tokyo, like when will Akka HTTP be the default backend in Play? And each year I was saying very soon. So this time it actually is becoming the default backend for Play. In Play 2.6, Akka HTTP will be the default backend, which gives all of these streaming features to Play just by default. and Akka typed. So all of the people who complain about not typed actors, we hope to actually this year, it is a team priority to focus on Akka typed. So if you're looking forward to that, now would be a great time to try it out and give some feedback, because we're going to make it stable maybe this year, like end of this year. We'll see. So this is the link to the free ebook I mentioned. It's just bit.ly why reactive, if you're curious. The slides will be available online, and if you have any questions, I'm happy to take them right now. Thank you very much.